Now is the time to take risk.
Yo, what's up, you guys? So this is a fun conversation with the founder of Cosmic Shielding. Now, most people think that water will be a good shield in space or that we could just go underground to avoid radiation, but water is heavy and digging underground is not easy. And lastly, most of the radiation concerns are focused on primary radiation and not secondary radiation, which is caused when radiation particles hit shielding on the ISS, for example. It breaks into more energetic particles and is more dangerous. So what if there was another solution that was lightweight, you didn't have to dig underground, and it also prevented secondary radiation? Well, obviously that's what this team is doing. That's why I'm talking about this. And his team is solving this by building a very versatile material. Like, for one, it could be used as shielding on the ISS, but it's also flexible and light enough to make astronaut suits out of this material. And it can even be like manipulated enough that you can build a rocket out of it, which I had never heard of building like a radiation shielded rocket. I'd only thought of like putting radiation shielding on the ISS after it's been launched on the rocket or something. But I mean, if we're going to be living in rockets while we're being transported to Mars, kind of need some radiation shielding, right? So anyways, he's crowdfunding for this startup. I was not paid to promote this. I just think it's an interesting company and I want to share the opportunity with you guys. I might be investing. I haven't decided yet. I'll probably add it in the comments below. And as well, the crowdfunding link is below if you want to invest or just learn more. And also the Spotify and Apple and all those links are also below if you just want the audio. Hopefully YouTube starts letting you just listen to audio only podcasts soon. I think they're working on that. But for now, just watch the video. Give me some watch time. I'm trying to get monetized. But seriously, just comment if you think anything's cool. Toss a like if you're feeling super generous. And without any further ado, here's my conversation with Yanni, the founder or the co-founder of Cosmic Shielding.
Now is the time to take risk.
Okay, cool. We'll just start the recording. Okay. And it's Yanni.
Yanni, yes.
Yanni. Okay. Yanni, what's up, man? Thank you for being here.
Yeah, no, I'm happy to join on. I've been listening to a few of your podcasts and they're really good take on the deep tech industry in general, and then space particularly. I mean, there's been a lot of focus on the main players in space, from the general media when you're talking about Blue Origin,
yeah,
the Prime, SpaceX, and so forth. So it's always good to get someone looking at the nitty gritty of the startups that are actually building out the infrastructure technologies that we're going to need to live and work in space. So
yeah, I mean, SpaceX is providing the transportation. Now there's so many things that you can do beyond that using that transportation. It's so exciting. So like, I'm trying to make podcasts with all the coolest hard tech people that I can find. And like, your technology just seems like it's pretty essential to humans living in space and satellites in space and everything like that. So I appreciate it. And I'm glad that, I was actually looking if you had done a podcast too. And I'm glad, I think this is the first one that I could find on Spotify. So I'm glad that we're going to, expose what you're doing to hopefully a broader audience.
No, I'm glad too. You're actually the first one. And we had a few interested parties earlier on, but I wanted to wait until, things were more established. Now that we actually have launches planned and the technology is significantly more mature, we're getting client traction. I think now's, much better time to start, getting our kind of vision out into the world.
Yeah. I mean, so let's talk about your vision. What is the vision? And then let's talk about and then beyond that, we can talk about legacy and business and stuff, but what's the vision right now?
Okay. So the vision is big, right? And it's definitely something that may not, when people look at a radiation shielding company, they think you're just solving a very particular issue, and you're going to have a very niche application, but a widespread, but niche application. However, what our goal is, the way I see the current space industry, current spacecraft, right? Launch is important because that's the first stage infrastructure, getting things off the ground, right? Mm-hmm. Then you have on-orbit servicing, whether it's in the form of, repairs, orbital debris protection, and then refueling in space. All of these things are other layers of infrastructure. The one layer that I think has been not ignored, but has been getting less attention than it should is the materials layer. How do we build in space, right? And when we jumped into this market, our team is actually, everyone except me, I'm the youngest, right? I have some experience from prior startups and so forth. However, the majority of our team are pretty much the world-leading physicists, space radiation physicists, nuclear physicists, that have worked on radiation shielding principles and radiation transport, dosimetry, and so forth for the past 30 years, from JAXA, ESA, NASA, SRAG, which is a space radiation analysis group, and so forth. So they've been studying this problem for a while, and One of the interesting things, and I know it sounds like I'm going on a tangent, but I'll tie this back into why infrastructure, why materials matter in space. One of the most interesting things that I think people miss about space radiation versus what they think about shielding against like a nuclear bomb or a nuclear reactor, right? It's very different types of radiation. Nuclear reactors don't have extreme high energy particles, usually gamma rays and some lower energy protons and so forth. Now, the interesting thing about our CTO, Dr. Lembit Seaver, he actually is very well known in the field for studying target fragmentations, basically how these particles affect targets, whether it's just any element basically that is in the path of the particle, right? And one of the things that people seriously miscalculated, this isn't even that old of a issue, it's something dating back to maybe 20, 15 years, is that anything, and I mean, technically speaking, anything with an atomic weight greater than hydrogen produces secondary radiation, right? And it's somewhat proportional to the square of the atomic weight. So the heavier the element, it gets exponentially worse, geometrically worse, right?
And just to clarify, is this when radiation particles hit heavier elements? Okay,
Yep.
so when it hits elements heavier than hydrogen, then it produces more secondary radiation.
Yes. And yes, exactly. And it starts becoming an issue when you get to the heavy elements. Metals specifically are very, very bad when it comes to the production of secondary radiation. So bad to the point that whether you're using a thick aluminum shield or a frame, a tantalum shield, which is something very commonly used, or say steel. Yeah, steel is one I like to pick on, right? You produce more secondary radiation, more dose received in the target of inside the craft, whether it's an electronic component or a human being, than you would just being naked in space, right? So the problem with this is not a very well-known phenomenon unless you're very, very deep into the field. So a lot of radiation screening engineers are very, very familiar with this. And all the physicists are, of course, completely familiar with this concept. Now, a lot of the modeling systems that companies use don't really take that into account as much. A lot of them use old systems like Cream 96, Cream 2000, even the SPENDIS model, which a lot of companies use to do some radiation modeling of their components before sending them into actual testing, physical testing. The details of the models we'll leave out for now because I can talk about that for quite a while. But they had some incorrect assumptions made on the physics engine they use, basically. Lembit specifically actually developed an improved version of this, right? So they were seriously underestimating the secondary radiation. So for what they were designing against, yeah, it looked good. It looked like, oh, aluminum made sense. It looked like, oh, steel made sense. Tantalum made sense, right? Well, in reality, it's absolutely detrimental. And not only is it detrimental in terms of radiation, it also adds weight to your spacecraft. So then we had the idea, what would be interesting is theoretically a lighter material is better, right? And you've probably heard people say, oh, waters are great for radiation. The only reason is because of the hydrogen. Theoretically, if you had pure hydrogen, that would be fantastic, right? Now, as you can imagine, engineering a spacecraft with water or hydrogen around it, it's very difficult. There's going to be a lot of challenges with that, right? And maybe one day we'll have metallic hydrogen plates, but that's quite a bit in the future. Now, what we developed is a very lightweight polymer. It's a new polymer. Essentially, we developed a brand new polymer that can be very easily modified and doped to have different properties expressed in different layers continuously and with a smooth gradient. Right? That sounds very, very particular. Like it sounds like a very detailed and niche benefit. But what that does is that allows you to have a single material extruded from one device that can have properties that you need for thermal regulation, for radiation shielding, for mechanical strength, and so forth. So the reason this was interesting to us is because what we envisioned was imagine a future, right? Where in space logistics are a huge issue. So in space manufacturing, you want to limit the complexity of your supply chain, right? And having multifunctional materials, I think, is the first step towards that. If you want to get a a little thought experiment about it, or I don't know, an analogy, is I see this as the first step towards something like programmable matter. Something where you need one basic material to satisfy tons of basic applications for a civilization or a habitat or so forth. So basically what we want to do is we want to build full spacecraft frames, right? We don't build the engines. We don't build the fuel tanks necessarily, but we want to build the full superstructure of the spacecraft. Whether you're building habitats, whether you're building space stations, whether you're building satellites, whether the satellites are there for, like their little CubeSats, or you're building big communication satellites or mid-sized, like internet satellites, like you see thousands coming up now, or deep space exploration, things that are going to take us to the next,
suits.
And suits and spacesuits. Yes, we are actually doing research with NASA on the Artemis spacesuit materials. It's very early fundamental research, but nonetheless, we think this is the direction the entire industry is going to head, regardless of whether or not it's us. And there is the way I see the use of metals in space, right? And I'm talking about alloys as a structural element. It honestly, it's getting to the point where it doesn't make that much sense. It's more so rooted in tradition and very, very understood engineering properties of these alloys, right? And as you can imagine, going to an engineer and trying to say, hey, the aluminum you're always used to using, let's replace it with something brand new. That's a very difficult uphill battle, but that's what we're working against right now because it's something that's so well understood, thoroughly tested, and so forth. So this is one of the main challenges. However, the way I see it, with on-orbit servicing, high-powered computing, humans in space, right? The way we've been operating in space is nothing like the way we're going to be operating in space in the next 2 years, 5 years, 10 years. Yeah, it's going to radically change. Yeah. We're staying up there for longer. We're moving faster. We're doing more. We're having more sensitive payloads, yada, yada, yada. Now, the way I see that is back in the day before jet engines, aircraft were made of wood, right? Some of them had the cloth frames or wooden cloth, That was fine for the speeds at which they were going, right? Now, once they got jet engines, all of a sudden the mechanical and thermal stresses are just completely different. You need a fundamentally new way of building. Right? That's what I think we're approaching in space. So our goal is to lay the foundations for this and provide that fundamental building block that will allow us to do. Yeah.
So
live in space. Yeah.
Yeah. So when you say constructing ships out of this material, are you saying that we'll launch it with this material on the outside, or it will be coated on it later? Are you saying that this would be stainless steel?
Yes.
In terms of thermal properties and be able to survive going up through the atmosphere?
Yes.
That's pretty crazy.
Yeah. What we can do, what we've tested, and we actually have a launch plan for and some client traction with I'm not going to hint any more details besides things to do with the moon and things to do with satellites and satellite servicing, right? Now, our material currently in its current state can handle the stresses you'd have in a satellite, right? Something that's going to be within the launch vehicle. Mm-hmm. We think within about 6 months to a year, we're going to have a variation that can handle the launch stresses for the full structural replacement of a launch vehicle.
So that takes 3D printing rockets to a completely new level because you 3D print this material as well.
Yeah. And think about the benefit on your supply chain, right? Imagine, the way I see the space industry, and I hope no one gets pissed at me for saying this, but when you're buying a car and back in the day, you add a GPS and it's $3,000 for a GPS, right? You're like, why are they charging you $3,000 for a GPS? There's kind of a markup based off the value of the end product you're buying, right? A significant markup. You're buying a house, you want a small modification, all of a sudden 5 times the price of what the same device bought off market. A lot of these very simple components that you have for satellites, I'm talking about aluminum boxes that they build, or the manufacturers that make the actual buses, the guys the Nano Avionics of the world, the Airbuses, the Northrops, and so forth. A lot of them buy these metal pieces for a significant markup, and they don't really provide anything beyond a basic structural element. What we're offering now is a way to get your core structural elements satisfied, plus enable unprecedented flexibility with the payload, right? And this is interesting when I say the supply chain, right? We're 3D printing this composite. And that, oh my God, that has posed a lot of challenges initially. This past year was just getting some of the 3D printing techniques to actually work was our main challenge. Now we validated that. But luckily for us, I think the timing was perfect because a lot of the legwork in the 3D printing world was already done, thankfully, right? Mm-hmm. Now, the filament we have, the interesting thing when you think about the supply chain, right, is the filament itself, storing and that, having excess inventory becomes a much less expensive problem with a single multifunctional filament. Because whether or not someone wants to buy an avionics shield or a CubeSat wall or a panel for a space station, it's the exact same core component, right? Depending on how we extrude it, we can actually change some of the properties, right? And we actually have this government SBIR, it's an Air Force one, that we're going to be working on now, that basically is looking at transparent applications of this material. So even with different manners of extruding the material, we can turn it transparent, right? And you lose a lot of the mechanical properties. Don't get me wrong. There are trade-offs every time you change certain properties.
Yeah.
However, your supply, you don't need to have a crazy adjustment to your supply chain for this. It's all the same, right?
So just so everyone knows, it's kind of like a white, like an off-white color right now, and not opaque at all.
Yeah, it's like exactly. It's an opaque, whitish, off-white color. That's the. And there are a couple variations we've done that have some darker hue to them, just based off different doping elements we've used. And that's currently what it's like. Now, when you get to the launch vehicle, it's going to look a little different. I can guarantee you that, because you're going to need some additional coating on the surface to take the like 2,000 degree heat you're going to need to withstand, and then like traverse the atmosphere.
Are you planning for that coating on the surface to like disintegrate while it's going up, and then you want, like, is it going to be reusable multiple times?
Yes. Or okay, that's the goal. Yeah, that's a goal. We're trying to find a coating. So basically, think about the coating to be less like a paint, more like something bonded just to the outer layer, like chemically to the polymer. And they're the Svetlana and Lembit, our lead scientists here, are playing with a bunch of different doping elements. But again, it's not our immediate priority, but it is something we absolutely want to solve, because it opens the door to quite a lot of changes in the industry. And then one of the benefits is our material is a little less than 3 times less dense than aluminum. So you get weight benefits.
How does that compare to steel, like the stainless steel that Starship is using?
Steel, I think that would be about like 4.5 to 5, if I'm getting it right, the density of steel. Yeah, something like that.
Okay.
And the good thing is the tensile strength of the ultimate tensile strength of material is about 10 times that of steel, right?
And so how does tensile strength matter when you're launching rockets?
So the tensile strength isn't the most important thing when you're launching rockets, but it does have some benefits when you're building structures and so forth. But the Young's modulus is also is a little better than what you have with steel. Some impact resistance is improved versus Kevlar, about 30% better in terms of penetration depth of micrometeorites.
Could you explain the Young's modulus just in case?
Yeah, for sure. So basically, that's essentially a very simple way of looking at that is how good is it at holding itself up. So if you get a stick of it, and you just hold it like this, how long can the stick get before it breaks under its own pressure? It's a crude way of thinking about it, but it's close enough. So as you can imagine, for aircraft design, that's extremely important, because you want something that's very lightweight but can hold itself up, and that ratio to be ideal, right? So the idea is we were focusing on these mechanical properties because we knew the radiation shielding properties we'd need, right? We knew how to develop that. That was our bread and butter, or Lembit's, our CTO's bread and butter for decades now on the rest of our team. Then with our team member, Svetlana Boroskina, she helped immensely with our understanding of the manufacturing process. And together we came up with a way to preserve ideal mechanical properties, thermal properties as well as those radiation shielding properties. But what's exciting to me is the point we've gone so far in just a year has been kind of incredible. And I'll be honest, like one thing that has been immensely helpful is that we got a very, very good investment team together. Like we have essentially backing from all of the American space venture capital groups. And what that has allowed.
Could you name a few?
Yeah, Space Fund, Helios Capital, World Quant Ventures, Space VC. Yeah. And then Seraphim now is also a partner with us. And this has allowed us to basically, one thing that people I think tend to understate as an important facet of growing a company is your image and PR. Right, even early stage. It's not just about your technology, right? You could have cold fusion, and if you don't have decent PR, you're actually not going to probably not get funded for it, right? So luckily, when you have the backing of these VCs, right, like we have our team's academic background and scientific background is very well known, right? However, when you translate that to the business world, that's not the metric they're looking at, right? It's the technology's viability in the market and the ability for your team to scale the technology, right? Having such backing from our VC partners has not only allowed us to like have that appearance of good floor to stand on, essentially, but the partners themselves have actually provided us with some unprecedented agility in being able to find ideal potential customers and actually get direct meetings with the key stakeholders just like that, right? And our PR has almost taken care of itself in that respect, right? Just by having these partners on our back end, because it's like a network effect. The more you get on, the more buzz builds around you. I mean, don't get me wrong, on this next stage, this next year, PR is going to be a massive focus of the company, because there's a lot of, I think, education that has to be done to make the very detailed metrics for understanding radiation shielding to, to actually hit with our clients.
I think getting on Twitter is going to be important for that.
Yes.
That's just so everybody knows, I got him to sign up for Twitter so we can communicate. I think like communicating that is going to be very important for dispersing like the ideas, because definitely people do not understand secondary radiation at all.
And I'm using simple terms for it too. Like when Lembit explains it, oh man, like I've been immersed in this for quite some time now, and I still, miss things here and there. And it's definitely going to be it's going to be a fun experiment trying to figure out how to establish true thought leadership in a way that's very simple to convey and so forth. We have some ideas on little like kind of programs and such that we could provide to kind of illustrate the different types of metrics you look at radiation. Like, oh, total ionizing dose. People say, oh, total dose makes sense. It's just one of many metrics. You have the LET, the track structure, the deposition in the material itself, and so forth and so forth. There's many different measurements you have to take into account when trying to determine how good a shield is, right? Mm-hmm. And on that note, there's some interesting, for example, pushback we had initially when people were like, because we mentioned we can provide protection against GCRs, right? Galactic cosmic rays, which have been notoriously hard to shield against. So a lot of people are like, oh, that's impossible. The moment someone starts talking about shielding against cosmic rays, it's not.
So is that what's produced when a solar flare occurs?
No, GCR. Oh, it's funny. So GCR is actually produced from stars, but not our star. It's produced from supernova of other stars, right? Bouncing around the galaxy, then create a basic ambient background radiation, right? Mm. And whenever we have more a solar flare, actually, it reduces the dose you have from galactic cosmic rays, because the solar wind actually pushes and creates a little shield.
Oh, okay. But it still has other damaging particles.
Exactly.
And you can also shield against those.
Yes. And the shielding technique is much more complex against GCRs, right? So those GCRs are made up of many different types of particles, right? The vast majority are protons, extremely high energy protons that basically don't really interact with much, right? They just kind of fly by because their energies are so high. Then you have heavy ions, which are actual elements, like little iron ions flying at near the speed of light. When they impact the target, they impart an extreme dose in one localized area, right? And this is kind of getting into too much of a lesson, but there's one.
No, this is great. I love being technical.
Oh, so the total ionizing dose, for example, with particle radiation is not the best measurement, because a lot of the issues with particle radiation is the localized dose, right? Mm. And basically you can have something that appears to be, a dose of 50 millisievert, right? Not that bad, right? But locally on a, whether it's transistor or DNA strand, you could have a dose of 1,000 sievert, right? Which will destroy it.
And it's diluted to 50.
Yeah, when you look at it as an average, right? And it's because some issues with like how they detectors used and improper analysis and so forth. Not incomplete analysis. Don't want to say improper. So basically what you can do with the heavy ions, without getting into too much detail for like trade secret reasons, what you can do with them is we can block a few, right? We can block certain heavy ions, like the iron ones are kind of easy to block. All right. Some of the other ones, what we can do is we can reduce the quality factor, which basically is how much energy do they impart on the target. And that is a very fine measurement, and it's a very difficult concept, because you lower the energy just enough and you're going to make something that wouldn't have damaged your target damage your target just because it hits a threshold. You lower it just enough beyond that, then it's not going to do any damage. Now optimizing the thickness for that purpose and optimizing the gradient of our material was one of the biggest challenges.
So why are iron particles easy to block against?
They're easy to block just because they're heavy. They're very massive.
Okay. So they don't slip through very easily. So then when you say gradient, can you kind of explain what you mean there?
That is basically, so not too much detail because that's getting into trade secret territory, but basically what we came up with is a continuous polymer-based graded Z shield, right? So what that means is we came up with a way of, very, very rapidly and smoothly transitioning between atomic weights to play with the target fragmentation to the point where you get a very good shield, right? So we purposely induce some fragmentation and then other things within the material. Yeah.
So like, to kind of, for me to just kind of repeat that,
Sure.
what you would do is you would take like a heavy particle that hits, and then you fragment it on purpose into smaller, like lower weight particles. And then throughout the gradient, it like keeps fragmenting it until it's essentially low enough that it won't go through like the last part of it.
Yeah. Something like that. Something like
Okay.
that. And with the GCRs, you do get a lot of them still going through. The protons, they're all going through. Not all of them, but a lot of them. The heavy ions, though, when people hear about like the single event effects, all the scary side effects that might happen to the astronauts, that is by far the culprit is heavy ions. So the heavy ions are what we focused on for GCRs. Right?
Can you block photons using any method, or
photons? Yeah, the photons are very easy. Photons, you just kind of like want a good metal shield and so forth.
Okay, I know you were saying it wasn't blocking that.
I said protons.
Sorry. Okay, so
Yeah.
with the proton, what would block that?
So the problem with those protons is when you're talking about the GCR protons, like those ones can get up to extremely high energies to the point where they're not really even interacting with matter. So for that reason, you don't need to block them actually. There's some you just don't need to block. And then there's some that contribute to those that there isn't really, they're just at the point where you're going to need very thick shielding. Like, for example, if you're talking about lunar regolith, right? People talk about lunar regolith. This is actually one of the things we're kind of proud of. So if you did say you have a moon base or a Mars base, right? To get shielding to like sufficient shielding against GCRs, and this doesn't include all the protons, right? Because like I said, those things are notoriously hard to stop. But some of them, and then some of the heavy ions, you're going to need meters of shielding. Like I'm talking meters. So that's why they say underground might make sense, right?
Mm-hmm.
But a lot of the initial calculations of some people say, oh, you only need to go like, a few feet underground or like, 6 feet underground. That doesn't take into account the secondary products, the neutron radiation, which is one of the side effects of that target fragmentation, right?
So the regolith is fragmenting it.
Oh, yeah.
Making it more damaging.
Exactly. Regolith is filled with metals. There's a lot of metal oxides in there, right? A lot of heavy enough elements to cause enough fragmentation to be an issue. So it's not an efficient shield. It's just available technically beyond the moon. Now with us, say you were to get to like this isn't something you'd want to do for a spacecraft, but if you had maybe like 10 inches of shielding, you could probably have an environment that's similar to like kind of like and this is like a GCR environment to like what you'd have on an airplane, like a low flying airplane on Earth, right?
Okay.
Now, but the thing is, the gains are a little depreciating past a certain thickness and appreciating below that thickness in different ways. It's kind of weird in how it works. So I'll give you an example. Like,
okay,
if you want something to live long enough to fulfill, like stay within the radiation dose limits that are set by NASA, ESA, whichever one, right? They're varying now, and they like fluctuate between 600 millisievert lifetime, 1,000 lifetime, right? You're going to get that within a year, or on the way to Mars. You're going to get that. Right. On the time it's going to take you to
using traditional methods,
right? If you had about 3 inches of our shielding, we could probably get you there, and you could probably stay under that limit for a few years, right? Like maybe 3-4 years. But that's not crazy. Like 3 inches, this much shielding,
mm-hmm.
right? And when you consider the density, the lower density, you do get some benefits on the weight. You get, or it's equivalent to maybe an inch of aluminum shielding. A little less than an inch of aluminum shielding. Now, when you're talking about it,
how thick is your prototype right now?
The prototypes we built up to like inch.
An inch. Okay.
Yeah, but the ones we produce mostly are very thin, just because we're testing like mechanical properties in production.
Yeah.
Techniques.
You have proved that you can scale it.
Oh yes.
Thickness. Yeah.
Yes. And the trick though is, can we do that very quickly? So we're going to find out over the next few months. Like, can you like do this on scale with a large vehicle with a rapid 3D printer? Is it going to maintain the properties you want? We think yes, but again, this is going to reveal itself very soon.
Mm-hmm.
And yeah, generally speaking, what's exciting to me is that it's the flexibility. And when you're talking about shielding, like when you're looking at the new missions that are coming up, like people talking about on-orbit servicing, the great. Okay, like fine, on-orbit servicing is fantastic. We're going to need that, right? The problem is the vehicles that are going to be serviced, or currently, right, we're not designed to have their operational lifetime doubled. Actually, for most of them, if you did refuel the whole thing, they're not going to last twice as long. You're going to get
because their shielding is decaying while it's in space.
The components on board, yeah, the charge buildup and the damage to the components and so forth aren't going to last. And the funny thing is, this is why we use older chips for like GPS satellites, a lot of them use like equivalent of like an Intel 8088, I think 8080, what is that old, like, 80s, 90s processors. Because large transistors are naturally more resistant to the particle radiation.
So 5mm manufacturing is not built for space.
Yeah, exactly. No, exactly. The newest cutting edge components are just progressively more vulnerable. And this is something that is very like lesser known as well. Quantum systems are significantly more vulnerable to space radiation than current systems.
And so you're saying that with your shielding, you can enable 5mm or quantum to operate safely because it's shielded from the damage.
That's the idea. Yes. And we haven't tested that yet in like a fry and die testing because there hasn't been that equipment there to test yet. So we're going to be doing some demonstrations with high powered computing satellites over the next year to showcase the ability to use, because, Earth grade components, like things you have in your cell phone, the chips you have in your cell phone and your like a gaming desktop, for example, is by far faster than any system in space.
Yeah,
quite a long shot, right?
Yeah.
So a lot of the companies looking to build like edge computing in space have been coming to us for assistance on building these enclosures and so forth to protect.
So do you know what kind of components like Starlink is using? Like, are they enhancing their shielding, or are they also using like legacy components? I'm just curious, like how SpaceX approach differs from typical satellite approaches.
I don't think are an exception to this rule. Most guys have been using redundancy when they're using COTS components and taking the churn rate of the craft's lifetime being short. So basically they have the ability to stay afloat while having to replenish the satellite constellation often, right? And within the satellite itself, what my understanding is, it looks like probably some redundant system. So if something fails, you have a backup and a backup and so forth. A lot of companies have been doing this, but then again, even the backups degrade as well, right?
Yep.
Just more so to like make sure that the error rates, the faults you're having from like seeing like, bit flips occur, single event effects occurring, you can at least tolerate those, right? But it really doesn't do much in the way of degradation. So that's where the churn rate economics come in.
Okay, yeah, and Starlink is LEO, low Earth orbit, so they degrade within a few years, and then SpaceX can just pretty easily launch them more. So it's not a big problem.
Exactly. And in LEO, the environment's actually a little higher than you'd expect. It's not nearly as bad as GEO, of course, or outside the Earth's magnetic field, but it's still an issue. And I would say that it's actually less than a couple years, if I were to guess.
Okay.
I know that I've heard things saying that, a lot of these COTS constellations are lasting less than a couple years. But yeah, this you could theoretically eliminate the need for any significant redundancies and so forth on a hardware level. Right?
Okay.
Which is cost, weight, so forth.
Okay. So I want to go back when you were saying that this is a polymer, and you were saying that using hydrogen would be the most ideal because it has the lowest atomic weight.
Yeah.
What is I don't know if this is trade secret, but like atomic weight of the polymer, does that come into play? Like, were you concerned about that when you were building this?
Yeah, no, it was specifically designed, to maximize hydrogen content, but also to be able to, so basically, with the polymer, depending on how you dope it, if you put in different, you remove a hydrogen, for example, on a hydrocarbon chain, put in a different, like a metal, say, right? You change the material, right? So that's all I'll say, right? We changed a polymer to become a fundamentally new polymer, but it is a hydrogen-rich polymer, and that's, we have to stay away from too many details there. But I'll give you an example, like the benefit of the production technique and the grading, for example, like very commonly known shield for galactic cosmic rays, heavy ions, is polyethylene, right? Polyethylene is extremely hydrogen-rich, right? But because of there's also limitations on just pure polymers, pure hydrogen-rich polymers, where you have an ability to protect against other types of radiation. It's not as necessarily as good for certain other types, like, certain solar particles, trapped electrons, and so forth. It's not really that great. So what we did is basically across the board, what we did with the grading that we've done, and specifically the doping, what it allowed is to get GCR performance exceeding polyethylene, which from a plastic standpoint used to be the best of the best, right? Not by a crazy amount. For example, in TID reduction versus polyethylene, you get around like 14%, right? But in the quality factor improvements you have on like how damaging each particle is, that's a very notable improvement. But the explanation there is long. Now with solar particles, trapped electrons, trapped protons, we exceed polyethylene by around like 60% in total dose reduction.
Okay.
However, the weight is not that far off. That's a good thing. You know, it's marginally heavier than polyethylene.
Because you're adding those metal ions, but it's not. Yeah. What's the weight percentage increase? Is that like 5%?
It's it varies depending on the type of it. Like for example, you could 10%. I'd say 10%.
Okay.
Yeah, that's very rough, but yeah.
Yeah, that's not bad.
Yeah. So basically, inspired by an old polyethylene-based shielding project from NASA, we developed a new polymer. The new polymer provides significant mechanical benefits as well as benefits on the other shielding requirements we need. For example, like even gamma rays and some X-rays, we do provide protection against, even though they're, you know, because of some of these doping elements we have.
I guess we weren't really talking about X-rays. Why are there a lot of X-rays in space?
Nothing.
Yeah, go ahead.
Yeah, not in the sense of like when you're worried about like damage, but when you're talking about like sensitive instruments and components, you know, wanting to shield against EM radiation is good for reducing noise and so forth. That's where that comes into play.
Okay.
And so we designed it to basically, because of some of the dopants we use are metals, right? Just in extremely sparing amounts. It provides some benefit against EM radiation, just because you're creating kind of like a Faraday cage or inlet device.
So speaking of X-rays, like, would you have Earth sales as well? Like, would you just sell to X-ray technicians to like scale up?
Okay, I'm glad you asked that question. Absolutely. So we're actually, one of the benefits, I think, and this is like, I'll get into this in a second. This is my personal big vision for the next, like, 10 years. But first of all, yes, there are direct applications for military applications, whether you're talking about like wearables, for example, like, high strength wearables. And when you're talking about aircraft could provide benefits just because the raw material cost is extremely cheap for us. So we're able to produce, the production adds quite a bit of cost, but it's still competitive, I think, with a lot of the aerospace outputs you're seeing.
You can make it cheaper than aluminum or whatever they're using.
It's not going to get cheaper than aluminum because aluminum is extremely cheap.
Yeah.
But it'll definitely be very affordable. It is. Yeah.
Not 2 or 5x more.
I'll tell you, it's right now it is. So right now our cost in the lab is around $900 per kilogram.
Okay.
This is at a lab scale. And we think by next year, probably by next spring, we can get that cost down to like $400 a kilogram. And theoretically, we think it's realistic to get to maybe 100.
And just for reference, what is aluminum or the alloys that they're currently using?
So if you're looking at the aerospace grade aluminum alloys and looking at the sale price, when companies buy like the enclosures of these, it's actually in the same ballpark. It's beyond 1,000 a kilogram. The raw materials cost though, and this is when I was telling you that analogy about, when you buy a car with the GPS, like that's kind of how I feel the pricing is determined here. It's when you look at the raw material cost, aluminum, it's like $4 a kilogram. So it's much cheaper, right? Yeah. But there's performance differences. So
yeah. Okay. Yeah. So you'll definitely have a margin to play with.
Exactly.
And then you'll be a startup and you won't be like a legacy ingrained in your legacy prices or anything. And so you can kind of compete on that sense. And then you're also providing more materials using more benefits using your materials.
Exactly.
So then on Earth, you're planning to sell to military for planes and other materials. And then I think I interrupted you. Was there more to that first vision?
Yeah, for the long term, yeah. So what we want to eventually do is, well, again, this might sound crazy, but I want to tell you my personal.
I love it.
One of our things that we're looking at, and one of our goals, personal goals, is to get towards an effective in situ system for producing this polymer, right? Because a lot of the raw components are readily available, and maybe not completely readily available for very specific aspects, but things that you can really reduce the amount of material you need to take from Earth, right? The reason I think it's exciting for looking at in situ applications is because it would allow us to stretch the multifunctional aspect to the max, like to its peak, right? Because imagine if you had with one filament, you can make it either as conductive as air, right? Electrically speaking, or all the way to aluminum. Now that sounds crazy. That's really interesting. That you can do that. That's actually possible, depending on how you orient the crystallinity of the polymer, how you orient the chains, and so forth. Now, imagine with that same material, if depending on how you, again, in simple terms, how you build it, it can be yellow or it can be green or it can be red without a dye. Same thing. You can actually do this
without a dye.
Without a doubt, just by modifying the chain length of the polymer and so forth, and like how you get the crystalline and so on. There's a lot of details there that I kind of really brushed over, but we'll get there. So what I see is one day, right? What if you had this base material that replaced a lot of our needs for a lot of structural and, not highly specialized applications? Like, you're not going to use it for any computing resources for sure, right? You're not going to use it like to build actual chips. No, you're not going to use it to build like photovoltaic cells necessarily, right? But everything else, everything in between, like, the frames for everything, the actual, like, the like clothes, plates, glass transparent panels. Yeah, you could use it for that. You need mildly conductive thermal regulation that doesn't have to be the pinnacle and performance like what you'd have with graphene, but you still need it to be pretty good. You could do it, right? So I was thinking, if our goal is to eventually demonstrate, better flexibility and an in situ environment, right? Using some readily available raw materials on lunar Mars. And this is very vague because this is far out, right? We're still working towards this. The first step is multifunctional applications for satellites, right?
Yeah.
But what I see as the ramifications is these raw materials are cheap, right? And you can build a lot of the raw components for the polymers can come from things in an atmosphere, things in the soil, right? Now, this is the crazy part. And I don't think it's that far. I don't think it's absolutely unfounded, but personally, I think one day, maybe 20 years from now, this might make sense, right? But when you take these plastics, these super high performance multifunctional plastics down to earth, right? Something that was designed to last a long time without degradation, because you have to have off-gassing resistance because you're in space. It's a vacuum. Something that was designed to take thermal stresses and so forth, not, combust and be dangerous because you have astronauts, right? If you took that back to Earth, that makes a lot of sense for houses and buildings, right? Cars, airplanes, like I said, but the houses and even, tables, 3D printers at home that can produce a much wider range of equipment that you actually use. 3D printers that, I don't know, could make maybe a stapler, like something that's actually functional and actually has little components that you use for another application and so forth, like, cascading functionalities. And what is really exciting to me is in situ manufacturing, right? I think could lead to better carbon capture technologies, right?
Okay.
Because what single filament multifunction composites, which is what we've never called it that before, but let's call it that, right? What that allows you, like when you streamline the supply chain so that you kind of decentralize a lot of manufacturing because you need less of an infrastructure to sustain it, right? That allows you I think each location's resource draw is going to decrease. And if you can get a lot of the raw materials like the hydrocarbons from the atmosphere, right? And you don't need to get much else from a supply chain, then that might become economical, right? And that's very big. I'm not claiming it is, but I'm saying I see a path where that actually might make sense. So you can stimulate an industry potentially, right? If you knock down a lot of the problems we have with plastics, like, a lot of plastics, microplastics are a huge issue for the environment, right? If you design robust plastics that have minimized a lot of the downsides they have, the thermal issues, the UV degradation and so forth, which you have to do for space, right? Then maybe you can drive the industry on Earth to be much more plastic centric. And while that sounds like a bad thing at first, if we start building things with permanence in mind out of plastics, right? I think it's going to just drive up it's just going to make us think more creatively of where these raw resources come from. So it's going to shift oil from fuel to an actual material, building material. And eventually, hopefully, from oil, you go towards what's in the atmosphere. It's a crazy idea.
What's the composition of plastic? Is it polyethylene that's just not manipulated, or?
There's a lot of different types, but yeah, carbons and hydrogens are usually.
Yeah. So when you integrate the metals into this polyethylene, is this going to massively proliferate like microplastics, or are you saying that because it doesn't degrade as much, then it won't dissolve into the world and infiltrate us?
Yeah. So my guess, right? And by the way, we're not using polyethylene now. Actually, it's basically it's a different type of chain, but you have some similarities in terms of hydrogen content. So now we have a new polymer. So like, traditional doping is you just have polymers layered with each other, well, and then maybe an oxide in between, but it's not chemically bonded to the polymer. So we have a new polymer fundamentally, right? So it's no more is it polyethylene, but take that example, right? What I see is like, sorry, I lost my train of thought. So basically, what I'm thinking is that the can you repeat the
Yeah,
question?
we were talking about microplastics degrading.
Yeah. Oh, sorry. Yeah. Okay. Yeah.
Yeah.
I just started thinking too much about chemical composition. Okay. So yes, the good thing is like microplastics come from like degradation of plastics and so forth. They break down and they break down into very small particles, these particles of that, right? So if you have, I'm not saying it's solved. By no means am I saying is this issue solved. But what would a scenario be where you can get tons of funding and economic funding? You can actually make money while doing the fundamental research to solve this issue in space, right?
Mhm.
Is to have plastic satellites, plastic spaceships, composite-based spaceships. You're going to have to solve this issue. This is like similar to off-gassing and UV breakdown, right? You're going to have to build significantly more resilient plastics. And we're currently working on the UV and off-gassing issues right now, right?
Mhm.
We have some very good performance in that regard, but I think give it a couple of years, you might have craft that could last with minimal degradation for decades, right?
Mhm.
And
So then also, if we use these resources on Earth, like you were saying, cups, or it would be leaching microplastics.
that's the
I'm
idea.
very passionate about microplastics.
Yeah, no, that's the goal. That's the goal. And like, that's one of the issues with using plastics, like right now, of course. Yeah.
Yeah.
And me too. Like, I also like, yeah, I'm big on climate change, big on sustainability on Earth. And what I'm hoping to do with this is actually use our technology to drive significant sustainability on Earth, right? I want to find a way, like, and this is just me personally, right? And who knows if it'll happen with CSC alone, right? Maybe it'll take 10 years. I don't know. But I think there's a way to drive the economy here to start looking at this like carbon sequestering and, just methane capture as a way to produce what we build our society out of, right? And I think that's one of the easiest, big quotes, easiest ways you can drive a large scale change fast enough to reverse some of the climate effects we've been seeing.
Are people making plastics from carbon capture? And I know we're off the space topic and we'll get back to that, but are people making plastics out of carbon capture, or like, would your method be easier than what it currently is?
That's the thing. There's like, I actually don't know too much about whether or not there's been a ton of research into actual like, large scale production.
Mhm.
I know like you can theoretically, and this is where we have like this big risk. Theoretically, it's possible, right? And there are some techniques to, for example, capture methane, right? And turn methane into oil and turn oil into plastic,
Yes.
right? So I'd say in that regard, yes. Now, if there's new smaller groups who are actually studying direct, like some more direct like applications or techniques, I'm not sure. And that is very, that'd be
I
great.
think I'm very bullish on carbon sequestration becoming more profitable in the near future. I don't need to go super into it, but there's this thing called Clima, which is like essentially buying up carbon credits it's a crypto thing. And I think the price of carbon credits is going to increase. So carbon emitting is going to be more expensive, and carbon sequestering and selling those carbons is going to be more profitable. So I think there's going to be a big boom there. It's launching in like a week. So it's
that's awesome. No, I agree though. I completely.
Yeah. So then just to summarize that kind of section is that the plan is ISRU on Moon and Mars, practice carbon capture, practice materials, and then bring it back to Earth so that we can kind of have decentralized carbon capture with a printer next to it that can switch over various types of these polymers, like with different properties, and then produce it for a micro supply chain kind of thing. Exactly. Yeah, that's a pretty bold vision. I really like that.
And it's the first step. I'll tell you, the first step was to show that, first of all, our shield can work, right? So luckily we've established it. It's by far the best in the world, right? However, then this next step was, okay, well, people want to buy it. Finally, in the past month, we've actually got our first sales, right? Mm-hmm. And these sales could potentially scale to large contracts and constellations. Now, with the closing of this new round we're doing, the $8 million, and then the $1 million allocation on Space Ventures is nice. We're going to be able to do some actual orbital production, or space-ready production, and our orbital demonstrations coming up, like I said, in June, right?
Mm-hmm. And just for context, this round ends in December.
It ends,
or unless it hits its $1 million target first.
Exactly. Yeah. So the overall round, we're going to be closing so basically, like I said, there's 1 million allocated on Space Ventures, 7 million from our VC partners and some new VC partners. That is closing in about a few weeks to a month. We already have the majority of the commitments in, and then we'll close the Space Ventures allocation in December, like you said, December 5th,
Okay.
I believe.
The crowdfunding. Yeah. Just that people don't know
crowd,
what Space Ventures is. Yeah. And that'll be linked in the description.
And one of the main reasons, because I'll say one thing that has been very lucky about this, we're not lucky, I guess we did work really hard, is that we have not had any problem raising capital, right?
Mhm.
And the reason is because it's a very pervasive issue, and we actually have a solution that's not crazy. You know, I'll tell you some crazier ideas. Magnetic shielding, you might have heard some people talking about active shielding, magnetic shielding. There's some fundamental problems there too. One, what do you do with the trapped particles? You know, like when you have the aurora borealis, those are trapped particles, right? They cause damage. So what do you do when your magnetic field is trapping these particles?
Mhm.
Second, right? There's physics issues that are still not worked out yet. So it's that's not just applied engineering right now, or engineering. It's a physics issue. Then the second is the power, right? You know, the Earth's magnetic field is, the intensity is like 0.25 to 0.6 Gauss, right? The smaller the field is, the more energy you need to have a similar intensity, right?
Mhm.
Like I think I can't remember the equation, but I think it might be exponential. So with a very small area, to have a shield that's similar in efficacy to catching trapped particles, that's what you'd have like for the Earth's magnetic field, which is what you need for a spacecraft if you're looking at magnetic shielding. Because anything lower than that isn't going to do a significant. I mean, you can help, but let's just for the time being, if you would build one that small, you would need an absurd amount of energy. I'm not saying it's not possible, and it probably will happen, right?
Mhm.
But
It's not 2021.
no. I think by the time that happens, we're going to be like space fair, like proper space fair.
Yeah.
You know, actual spaceships and,
When we have actual limitless energy and micro fusion reactors in our phones.
Unless there's some really fundamental break, or like really cool fundamental like materials or some other like, superconducting breakthrough that happens in the next 10 years. That might change it. I don't think so. Right? I still think the power is going to even present itself there, but
so what were other options other than the magnetic?
So a lot of guys are talking about water wipe shielding. They talk about the Regolith Insitu, right? Which can work, but if you use a combination of our shield plus the Regolith, you end up needing significant reduction in the amount of Regolith you need, so you can actually build above ground rather than having to go underground, right? Which I think is a benefit.
What would the depth of Regolith be with your shield?
So it depends if you're on the moon or Mars, but we think with about, this is like very rough because we're actually running for specific application. We're running some models to see the exact amount. But we're thinking if you had like, say you have like 2 inches of shielding, of our shielding, you could probably use another, and you had maybe like another 5 inches to a foot of Regolith, you might get some favorable results. We're not sure that. Yeah. That's uncertain. But I think what might be cool actually is when we get the lunar, so by the way, what we're doing when we say model, right? This isn't just like, small simulations on a computer. These are using supercomputer clusters, right?
Mhm.
And are basically modeling every single particle and interaction in the material plus the products in an actual simulated environment, exactly like you would have in space. These same models were actually used for the shielding on the Curiosity rover. They were used to design shielding for astronauts for NASJAQ. They're also used to determine potential danger to astronauts, for example, on the ISS. And they've also been benchmarked against actual detector results on the moon, in space, in geo, as well as on the ISS. So they're very accurate models. They're actually more accurate than what you get with accelerated testing on Earth, right? Now, you talk to most of the physicists, they're going to agree with you on trusting the models. You talk to a lot of the engineers, they might not, but I have my own.
When your CTO developed one of the newest models for secondary radiation, when did he develop that?
That was an ongoing project. So we developed one that's commonly used decades ago. And then the newest improvements have been an ongoing project since I think it was like mid 2000s. And then maybe he jumped off that project, finished up by, I could be completely like, getting this wrong, but I think it was around 2010-ish.
Okay. So
like late 2010, mid 2010s. Maybe.
So with those models, it seems like this problem kind of started coming to light. Was there some technology that was kind of not available before that was not available, but was necessary for this product to exist. And what was that? And when did that kind of come about? Like, is this something that was only possible as of like 2 or 3 years ago?
I'd say no. If you wanted to build a crude version of what we have, for example, and just have very discrete layers, maybe, and something like that, no. But with the techniques we use, yeah, okay, I guess you could say the printing technology has helped quite a bit. But if you ask the, like, very, very, specialized physicists here, like people who have worked with specifically space radiation effects on materials and bias, radiation dosimetry and so forth, these people leading the field, they probably would have been like, oh, of course, this makes sense. I don't know.
Okay. And so now it's more like, now that we're going into space, SpaceX has enabled the business play. So it's not necessarily, it wasn't technology of the material. It's more like access to space and like a market that you could grow on.
I'd say it's the market. Yeah. So I'll tell you this, because it's not just SpaceX launching. Well, yeah, okay, yeah, that's one of the main points. Yes. But yeah, a huge point. But actually, no, yeah, you're right. Sorry, take that back. It was very much so tied to launch costs. Yeah. So the reason the launch costs help is because it makes the design cycles for spacecraft, are a little simplified, right? I'm doing air quotes for anyone listening, right?
Mm-hmm.
They're not that simple, but you have shorter design cycles for companies using like, cheaper craft, single use craft, single application craft, so to speak. You have the barrier to entry into building satellites is much lower, right?
Mm-hmm.
Now, and operating satellites, more importantly, is much lower. So in tandem with that, companies have moved away from rad hard components because they're expensive, right?
Mm-hmm.
Let me tell you, if you have a $50,000 little CubeSat, why would you spend $40,000 on rad hard component?
And rad hard is radiation hard.
Yeah. And the cost was the initial drag, right? And that's okay, because some of these guys launching these small CubeSats, they don't care if it lasts that long, right? It could last a year for all they care, 10 months. A lot of the average lifespan, I think, is around 10 months for these small sets. And this is in the class of like 10 kilograms and less, which is not too tiny. That's a decent size. You can do a lot with 10 kilogram crap. However, I think what's interesting is the fact that, like, how do I say this simply? Oh yeah, sorry. It used to be the cost, right? And thanks to the use of these COTS components, the launch, it's almost dirt cheap to produce a little craft that can do high-end imaging, that can do, handle, when you're talking about hyperspectral imaging, when you're talking about communications. Now, add the new technologies that came out in the Earth market, right? You're looking at the advent of AI applications and consumer goods and SaaS products, and you're looking at robotics now becoming significantly more capable. Little things here and there that can improve the performance of a little spacecraft, right? A little bus, right? A little satellite. The computing power just exponentially increased, right?
Mm-hmm.
Now, when you want the performance, okay, then guess what? Rad hardened chips are very, very slow, right? So in that sense, it was indirectly for us, the rockets, right? The launch, but everything that it caused, like this cascading growth of the new space industry, the new space companies not wanting to use the traditional systems that were already in place. They wanted to save costs, but more importantly, want to do more in space. That's what that's what benefited us. That's where our timing, luck came in. So
that makes sense. So I want to talk about, how are you like 3D printing these? Like, how can you just give like an overview of that 3D printing process? Like, what techniques needed to be developed, or are you just like depositing layers on it, or how does that work? And then I also had but let's do that first.
So I won't speak too much on the process because this is going to change very quickly. So what we're using is basically Svetlana and Lembit have played with a very standard 3D printer. Like, it's a high-end one, but it's a high-end individual scale. Like, it's a lab 3D printer. It's played with the nozzles and played with certain aspects of it to take the temperatures we need and so forth. I want to be vague on this on purpose because we are now purchasing some large-scale printers, like industrial printers, to test our current techniques to see if they work on scale. But because what we wanted to see is, could we use our own filament without having to redesign a printer, right?
Mm-hmm.
Seems to be the case yet, right? But it is depositing layer by layer. We're using multiple spools and some other techniques to do some coatings at the end. And the printer itself, if you want to, it's actually funny. It's like a $2,600 printer successfully produced samples on. It's called a Ultimaker Connect Plus or something. Yeah, something like that.
Okay, cool.
It's a decent one, but what we think we will need to do is have a custom designed printer. Like, I don't think we need to do some fundamental research into the printer systems and so forth, but maybe like in terms of some of the mechanical setup of the thing itself, of the device itself. We're currently ordering, like I said, a few heavy duty printers, and these are like $100,000 printers that can produce larger volumes to actually produce some end products for clients, some early, products, as well as, test out the scale of this technique.
Okay. And then you have to manufacture, or you want to manufacture multiple properties or different material, or same material, but with different properties. Yeah. So how are you kind of like scaling first, like testing different doping methods? Like, how are you just like gathering that data and figuring out how to create those materials? And then how are you like working on scaling that process?
So right now we work alongside a lab at MIT. So Svetlana heads this polymer research lab at MIT, and we have a lot of access to like some benchmarking equipment. And because of all the benchmarking equipment we have available, it's accessible to do quick and rapid testing. Okay. Now, what we're doing is just basically tons of like iterations. Basically, we're just trying techniques left and right. Right. And that's one of the benefits of like, having a small scale, everything at your disposal on a small scale. Mm-hmm. It's like with the SpaceX, with the Starship, it helps to do some quick iterations and testing. So we do failure testing. We're just constantly doing failure testing on the composite and, pushing it to its limits, trying to improve. Right now we're working on melting point. We're working on doing some certain techniques to improve the melting point, and then the resolution at which we're printing at, making sure it holds its form, reduce any viscosity issues, and so forth.
Okay.
Yeah, it's just
mostly a manual. Okay. Yeah. Are there plans to? Yeah. Go ahead.
Yeah. For the thermal side and for the radiation, it's a lot of digital modeling. It's all model, right? And then on the mechanical and production, it's mostly manual. Now, I know there's some interesting companies that have come up with talking about like digital manufacturing prototyping, which seem potentially interesting, but I'm not too well versed on them.
Okay, I haven't looked into those too much either. Yeah. So now that we talked about like the manufacturing, the 3D printing, so I was reading the crowdfunder, and this product, like selling it once to a company is a one-time thing. But on the crowdfunder, you mentioned that you have this solar engine, which will look at weather or solar weather, and then it can be like a subscription. So this is kind of like building recurring revenue, which I think is really important. And then it's also building like a moat if you're the person with this scale, and everybody's kind of bought into that. Can we talk about that?
Yeah, for sure. So what's interesting is all of the companies we talked to, essentially all the big ones, have asked us if we can provide consulting or licensing of our modeling systems, right? And it's because they're nifty, right? I'll be honest.
They're what?
They're nifty. They do provide advantages in the design process. Now, the solar engine is an interesting one. So the same group that Limbit and some of our colleagues worked with to develop early shielding also developed the forecasting system that solar engine is based off of, right? So Dr. David Falconer is a heliophysicist, one of the leading ones in the US, who actually spearheaded some, how do I say this? It's like basically ways to do all clear forecasts by looking at like vector magnetographs from the sun. So basically readings from the solar dynamic observed around the sun's magnetic field, and creating a prediction model for the next 24 hours, 48 hours, potentially beyond. Right now we're at 48. We can't go beyond 48 with any like strong certainty, but it's something we're looking to improve. So basically it's just good physics on modeling the sun's behavior. And so it's a simulation almost, right? It is actually just like a simulation of the sun. And we run it every hour with new data from the SDO, and then output for all clear forecasts for X class, M class, C class, CMEs, fast CMEs, solar particle events, and so forth, right? So if you go to NOAA, right, it's actually, and you look at they have an option to look at a next day forecast, right? That's actually an early version of the system we're using, right?
Oh, nice.
Developed by David. Okay. So with the new one, has some significant improvements to certain thresholds that trigger it to trigger an actual warning and so forth that improve forecast efficacy, improve the false positive rate, false negative rate, skill scores, and so forth. So basically what it is though, is a nice tool if you're dealing with astronauts or something, some super high risk mission. Like, I don't know, you have an extremely valuable satellite that you want to make sure you shut down in advance of a solar storm to reduce any potential sudden buildup in charge. That's where you'd want not just shielding, you wouldn't actually need forecasting. There's a strong benefit. Now, you also have some governments now interested. There was that Pro-SWIFT Act that was passed earlier this year.
What was that? The Pro-SWIFT?
Yeah, in the US. It was passed in Congress. It was basically trying to do it's pushing for the development of resilient systems against space weather events. Right.
Mm-hmm.
So the power companies in the US, or sorry, not in the US, worldwide, are potentially interested in such a system. I know, you might have heard about this in Quebec in 1989, right? There was a solar storm that knocked out power to the entire region, right?
Yep.
And
go ahead. No,
I was going to say that the power company over there has actually been, funding and looking into some research in space weather forecasting and so forth.
Yeah, because what they can do is if you can detect it 48 hours in advance, you can turn off your grid.
Yeah, exactly.
To save it. So I made a video like a year ago about the Daniel K. Inouye Space Telescope, which is in Hawaii. And I think they were getting like the highest resolution of the sun, and they were able to predict that it was like 4 hours. And now with that, it was like hopefully 48 hours. Yeah. So, I mean, it sounds like you're doing this, but perhaps on a better scale or something like that.
Yeah. So the system's automated and functioning. What I'm actually going to be doing soon is we're going to put a little widget on our website that'll have a forecast for the next day. Mm-hmm. And it'll basically just be a nice graphical interface for people to see in each category of an event, the likelihood and so forth. And it'll update it.
And then eventually you'll start selling that.
So we actually do have a few companies interested in licensing the technology. So with that, it was nice to have internally, and some of the original inventors of the system are on our team, right? Mm-hmm. And because of that, we have access to the technology. We're able to get the rights as well. Right. And we also have access to the minds who developed it and are improving it right now. And we're currently improving it. We're going to be applying some machine learning techniques, which actually has none incorporated right now. And I think that might provide some benefit. But we have some interest now from insurance companies, which makes sense, and underwriters for launch vehicles, for satellites, and so forth. And as a company, what we're looking to do is find channel distribution partners to directly license the system to. And the reason is, first and foremost, we're actually a materials company, like I said. So for the immediate time, we do not want to distract too much from the development of that budget-wise and, energy-wise. However, the system is TRL9. It's already proven.
What is TLR?
TLR, the technology readiness level.
Yep.
TRL9. So it's up there. There's not much work to do on it. Just some minor improvements here and there. And
somebody just needs to take the data and use it. Okay, I actually have somebody that's perfect for that. I'll connect
for sure.
After.
100%.
They're looking. Yeah. It's actually perfect.
And one of our major investors is actually interested in potentially using it again, also for their services. So yeah, it's nice to have. We're going to obviously be able to use it ourselves and then provide some benefit for complete mission coverage if someone's looking for that. We have some plans for such a thing in the future.
Okay.
But yeah, that could be a way to generate some nice recurring revenue. And what's nice right now is for an early stage company. So direct hardware sales, there is a very large market for that. I expect maybe the market size 5 years from now, 20% market capitalization on it. That's probably in the few billion a year in potential revenue on the table, just from producing even small class satellites, not all. Just a small sats, so weight class from 50 to 200 kilograms, right? Now, what's exciting though is what we want to do potentially is create, and this is just an idea we have and something we're potentially interested in doing, is a lot of the companies that are doing edge compute, right? That want to do off-orbital computing centers, data centers for companies. We think that it might make sense at some point that instead of, having them have to worry about building their bus, building their actual centers and so forth, we could build and host their payloads in an already developed, heavily shielded enclosure that we can rent time.
In space?
In space. So think about
not an ISS, but a port.
A port, yeah. A small, a little small one. And imagine if you go to our website, It's actually funny because the little picture at the bottom is just a theoretical vat. I just wanted to get a representation of it. That
I'm editing the podcast to put photos over like
the
things. So if we talk about stuff,
I'll add a photo there. That's what I imagine it would look like. But what you could do with that is if we're designing the enclosure completely from the ground up, we can make it heavily shielded to the point where the radiation effects are complete afterthought. You don't have to worry about that. And if there were, the way I'm seeing it is with some of the more sophisticated launch vehicles coming up, some of the shuttling vehicles that are emerging, the deployment systems, I think it might make sense that someone could basically, you could have the shell of a vehicle, right? Power management systems and all taken care of. Someone could send their high power compute payload and it can just dock a blade into this box. And then once it's done, it just shoots it out and, they can get the next customer in. The way I see it is imagine like, what if you had, and I'm not saying it's the most valid thing. I don't know if we'll see, right? We'll see. Yeah. I think it's an interesting idea though, because think of it like warehouses, like super high-end supercomputers you have on Earth, right? They have very, very complex cooling systems and they have very high power requirements, right? So initially when a company's starting in the computing industry, they're not really too focused on necessarily building this entire super high-end warehouse. They have to work their way up to that, right? So I thought it would be convenient that if you're Dell and you're making server blades, right? What if you don't have to worry about the headache of building a whole warehouse and the power systems in the warehouse and all that? You just find the perfect one already there, and you just stick your blades in there, and AWS can then come and buy you and use your set out, something like
that. Okay.
But yeah, that's just one way. And early on, like to get there, luckily we've been getting some good traction on we're getting actual revenue now on samples. People are purchasing samples to do some tests. And we are now getting early contracts just to do some assistance on design, radiation-centric design for certain high-risk craft and so forth. But yeah, once we get this production technique demonstrated on scale, for the demonstration we have on the ISS is going to be a representation of a CubeSat bus, or not bus, CubeSat enclosure, right? And I think once that comes, we're going to be able to start fulfilling orders for actual enclosures for satellites on a decent scale to start.
So what are the big risks here? What worries you the most?
There's a few. So luckily, what's kind of super relieving is whether or not the production would work. Thank God. It seems to work, right?
And so is that validated just a few months ago?
Yes. Yeah. Literally 40 days, I'd say.
Nice.
Before that, it was like, are we even going to be that much better at shielding with the newest modifications to the system, to the grading and so forth? Luckily, yes. Okay, thank you. So those are two big, reliefs off my chest. Mm-hmm. So the next barrier was funding. Luckily, it's kind of amazing that that's not a problem, because I had to start it before this, and oh my, this is a lot. It's a lot different, hot startups than it is to be the ones struggling. So luckily, I'm extremely grateful for our supporters for that, for our investment partners and mentors and so forth. Mm-hmm. I think the big risk is, in the short term, right? And again, this is kind of balanced out by capital and being able to have early revenues, is the thought leadership in the market and basically breaking through traditional techniques in satellite construction, right? Because like I said, it's not an easy job to go and try to replace a very well understood and risk-free material as a main structural element in a spacecraft, right? So how do you break down that risk? First, you actually demonstrate small scale use cases. You work and try to get your let's just shield an avionics box, very low risk, low cost, and non-structural component. Or you also simultaneously launch a demonstration of an actual structural component working and operating finite space. So we're working on both of these things.
I already said I have one founder to connect you with. I have a second one. I can't say too much, but definitely a satellite protection thing would be necessary.
Awesome.
So I'll connect you with them too.
Oh yeah, I would love that.
So get some more data.
Yeah, for sure. And then I think the other risk is it's not yet. So we're kind of first to market in terms of having a produced working, super high-end radiation shield that's multifunctional. There's a couple companies that have looked at shielding. Specifically, I've seen a few competitors of course, that are basically backgrounds in nuclear power plants and shielding in that sense, which is very, very different type of shield.
Yeah.
So that's one thing that seems to be a communications barrier almost.
So you're saying like the people that might be working on this just aren't focused on this really at all because they're coming from legacy industries. So they're using legacy techniques.
Yeah.
You kind of approach it a little bit.
Exactly. And I don't want to be arrogant and assume that's all that's happening, because absolutely not. There's definitely probably some company out there that is going to hit what we have or get it like, or what's the expression? I don't know, uncover the the right order, formula, whatever, soon. Maybe in a year, maybe it's in 2. However, what we do have right now is a significant head start in traction and capital. So that's a nice benefit. What I'm worried about in terms of competition is not startups popping up, right? Because I will be frank, and I'm not trying to brag or anything, but the technical team we have is essentially the best you can get, right? And I mean, Lembit's the world leader in this field. And then from the material science perspective, so long as kind of, really, really top notch and data. Yeah. So we got lucky there. Not lucky. It just, it was, again, hard work.
Yeah.
But what I'm worried about are the big guys. Someone who has a very, very strategically inclined to see this as a fundamental barrier or step in their development, which you can probably think of a few where this might be directly relevant strategically. Those guys, when you have that kind of capital, okay, then there's kind of a problem there unless you're prepared. However, I think there are ways to, make it so that you're insulated against that from occurring. So I'll say, like, what I've been trying to do with our client acquisition strategy, right, is I think if you want to establish thought leadership, you want to make people rather use your technology rather than go through the headache of developing their own or making do with the next best thing, which the next best thing is, I'll be honest, a good step down. So at least we have that going for us. I think that what you need to do is show thought leadership. And I know I've mentioned this term so many times, but I think it's really important when you're trying to break down the barrier. I've tried this fundamentally new technology that is absolutely not like what you've been using before, but trust us, even though we're brand new, we're a year old, trust us, you have to establish, you have to lean into the technical expertise of your team. You have to lean in to the credibility of your team and backers to build off this idea that, okay, we can be trusted. So to do so, I've been focusing on clients that have a breadth, right? Companies that deal with very specific, specialized applications, lunar applications, right? Not necessarily where all the money is, but a very, very demanding situation, right? Then companies dealing with, habitation in space, right? Now, again, not necessarily the largest volume, high ticket, yes, right? Like stations are expensive, but very, very demonstrative of a core, a core function of the composite, right? And then where the money is, which is the computing and the satellite bus industry, right? It's, I think, a tiny bit of traction in each one with the right player can give us the credibility we need to start scaling a little faster. Because that's one thing, I think founders and investors sometimes disagree with. And then investors are usually right with. But, some founders, you're young, you jump into the industry, you think, oh, the only thing we need to not have to worry about competition is money, right? That's not true, right? I think it's a combination of the credibility and the capital, right? The capital just allows you to move quickly, but the fastest way to kill a company is to move quickly in the wrong direction, right? So as long as you are on the right path in terms of building your image, your credibility in the industry, you're actually hitting the right pain points that are the most, not necessarily the most profitable pain points in the initial stages, but very high profile ones. I think you're giving yourself the benefit of the doubt in the large manufacturers' minds, right? And that is what makes the difference when you have a competitor pop up that potentially is either more or equally equipped in resources and maybe somewhat competitive from a performance standpoint. Luckily, we have a grace period right now, but I'm trying to do all I can to make sure we're set up for sustainability and credibility. That's my goal for this company. I don't care about like necessarily crazy rapid senseless growth. It's the sustainability point. Because to me, the vision is bigger than just, it's not a quick buck. I'm not trying to sell this company quickly or do anything.
I was also going to ask, would you be acquired by one of the bigger companies once they start thinking about this?
I could see that being a situation. It's not my goal. To be honest, it's not my goal, but it would make sense, I think.
So usually I don't like to rely on patents, but like, do you have any patents? I'm just curious.
Yeah. So we have a couple old patents and we're filing several now, actually. We had some provisionals filed the past year. At the end of last year, we also filed a couple provisionals. And we're currently moving to file 2 full patents on those. And the details on which, again, we'll say for now, just because they have to do with layering and so forth. Now, one thing that's interesting is, there are a lot of angles for IP here. And we are doing as much as we can to cover production techniques, methods, compositions. However, I think at the end of the day, with the materials play, the key is to rapidly establish, like I said, the credibility and thought leadership, plus the infrastructure to produce. That's how you set yourself up for an acquisition. IP alone, I think, is okay. It's good.
Yeah, exactly. That's why preceded that with I don't like patents. Yeah.
And just so everyone listening knows, when I said IP alone, I was given like I don't think IP alone is not what makes your company secure. It's having the infrastructure that backs up that IP and the relationships as well.
So speaking of infrastructure, I mean, you have this team. Do you have jobs on your website?
Not yet. We will be. So by the way, I'll just publicly say we're going to be looking for some aerospace engineers, specifically with experience in satellite systems, subsystems, thermal engineers, and who else? I think for the immediate future, that's kind of what we'll be looking for. There will be descriptions listed on our website and LinkedIn.
And also, so I do have a jobs board. It's like palette.xyz/NASJAQ. And then I can link that below and I can add your jobs whenever. So we can definitely do that. But I'm curious, like when you look at hiring people, are you kind of taking the Blue Origin approach of hiring people with tens of years of experience, or are you taking like the SpaceX approach of like snapping people up from university, like convincing them to quit their jobs and build rockets?
Yeah. So initially the former, now it's a mix. Right? And initially the former, because like I said, the as you can imagine from the radiation physics standpoint, there were not a lot of young people.
Yeah, that's why I was asking, because
exactly,
like very old, and it's sometimes that I don't know what I can really say here, but like sometimes you don't want that. But
exactly. What we did is, so from a hiring standpoint, it's essentially been Lembit taking the charge there. Right? I think he has been the one completely vetting new team members and so forth from the technical team, right?
Mm-hmm.
And what we're looking for now, we're starting to hire more younger, super motivated, high energy personnel that are also very well qualified. We're looking at some candidates from MIT, Berkeley, and Caltech. Okay. And initially, though, like for some of the key personnel, they're established, like they are extremely established, and very known.
They'll run a team.
Yeah. Because what I think when you have that mix, and that's, I'll tell you something that initially, oh my God, this worked against me. Because just so everyone knows, I'm 27, right? I'm the youngest one by far in our company for now, right? A couple of our, in terms of like, the co-founders, at least, right? And in the space industry, you don't see just too many young founders in the hardware space making it or doing well, right? It takes a lot of usually people like, you have to have worked 15 years at Blue Origin and done blah, blah, blah before you had you a few $1 million. That's something out. So one thing that I think has been incredibly good is you see this at any field that you get to a sufficient like height and depth in, that people become a little, I wouldn't say pigeonholed in a certain way of thinking, but there's a little less flexibility and expectation to how they will be treated and so forth. So you have a lot of
asking for.
Yeah, a lot of people who are highly technical, and I've seen this happen before, way more technically qualified than I'll ever be, right?
Yeah.
Come in, look for funding, and just get kind of like shot down because they're not willing to speak the language they need to speak in the moment, right? The philosophy we keep in our company, I told what I said with Lembit, and I learned this from just having a crash in my last startup, right? Is that as for the purposes of CSC, we have absolutely no egos. This does not exist, right?
Yeah.
I don't know anything. You don't know anything.
I don't know anything.
Yeah. No one knows.
That is my approach every day. I'm like, man, I am just an idiot trying to make it. That is how I feel.
And you just have to, by having this mix of people with this real world, decades of experience, plus people are just super high energy and willing to try new things and willing to make fools of themselves, if you want to be honest, right?
Yeah.
You get agility, you get dangerous agility. You have the ability to move quickly, but also with experience, that I think is why we've been doing well. And it's funny because like, luckily now, I used to not get too much. I think I wasn't given that much of a benefit of the doubt initially, just because of my, well, as far as all these other space companies or company groups we've been talking to, I was just some guy, right? Now my team was really great, but I'm just some guy, right? However, now that we've kind of proved out the benefit of having that kind of diversity on your team, like both in age and backgrounds and so forth, now people are, like, well, I'll say we are one of the fastest growing space companies, early stage companies right now.
Are you, quick question, are you remote or?
Yeah, we're remote.
Okay.
Yeah.
Okay.
And it's funny because I was at the Space Tech Expo last week in LA, and I met one investor there who looks like they'll be coming on in our current round, right?
Nice.
And I just realized we were getting coffee, and I was like, man, like, I don't think I have met a single one of our investment partners in person besides you. And you just like, when I'm talking, I was just like, this is great. Yeah. No, it's been all remote now. He's going to be working in the lab alongside Svetlana now to just streamline some or speed up some development in Boston. And we might be building a facility in Texas, actually, in Brownsville near the Starbase.
Nice.
Yeah, I know the mayor.
That's exciting.
Yeah. And we're going to build this like small. It's nothing crazy. I'm not building a freaking Starbase.
You're putting roots down there. I mean,
exactly.
Man, I've been thinking about getting land in around there or something.
It's not a bad idea. I don't think.
Why Brownsville?
So there's some really good incentives for space startups to go down there, like reduce costs on certain aspects and so forth. But I also think if this is a bet I'm making on the area, like with the launch facility there, it's the Starbase, there's a reasonable bet that in the short term that might have a large volume of equipment going through it, right? Large volume of launches and payloads and so forth, right? Now, I think, and it looks like there is some evidence to suggest that other manufacturers are going to be moving to the area as well. Because if you're building factories, like one of the reasons there, the labor market is very good there, right? And then also the physical location for SpaceX was very good. There's a lot of raw materials connections in there. So I think we're going to have some of the larger satellite manufacturers potentially move offices there. And for a component shield system designer initially, right? And then eventually, hopefully, like I said, we're going to be building full satellite frames and vehicle frames. I think it makes sense to be near those guys, right? I think it makes sense to be able to have this rapid.
And the labor there is getting skilled too. Like they're learning a lot by manufacturing the Starship.
Yeah, exactly.
For sure. Yeah, I think that's going to be like Austin, and then I hope there's like a Hyperloop or something that goes down to Brownsville, and I think then there will also be the triangle with Houston, Austin, Dallas.
Yeah.
So Houston, Austin, Dallas, and then Hyperloop down to Brownsville. I think that's going to be like a mecca in Texas. I think that's going to be very big.
I think so, and I think with they also have it is a good shipping route that could pop up over there. They have like really good heavy industry, like I said. Okay. And they're doing a lot to like kind of revitalize the town, and make it, up to par with a tech hub that you see. And, what's interesting is, so first of all, I think a nice additional public transportation down there would be great. Yeah. They do have a new airport, right? Which I did fly into. It's not bad at all. It's actually kind of nice, very new. It's small, as you can imagine. It's a small town, but the airport is very modern, very nice. However, there's not a lot of flights down there yet. I think that will improve in the near future. And what's interesting to me is just the potential, because like I was in middle school and high school in Huntsville, right? My dad worked at the Marshall Space Flight Center. He was a physicist there, and I remember that city. Like we learned about the history of the town, right? Pictures of Huntsville before kind of NASA came to be is kind of like what you're seeing in Brownsville now. It's like that industry completely changed up the town, and it's like the degree of like wealth for the general population, right? The infrastructure, and then the security as well. Because like the space economy is not like other economies where you're extremely resilient to any fluctuations in the economy, as you probably see. Like it used to be like very much so because it was mostly military contractors and so forth. So like, for example, in the financial collapse, Huntsville did very well because the majority of the jobs, like the big job supplies, were, military applications and so forth, things that weren't really getting cut as much. But I think Brownsville's going to see a similar situation pop up over the next few years.
Yeah, I grew up in Houston near the space center.
Awesome.
So I kind of understand.
You get that? Yes.
Yeah. Definitely had a lot of, like, an astronaut was my neighbor, right? Like,
exactly.
Really cool. And I could see that, it's funny. A lot of smart people were there.
Yeah, so you probably had the thing where someone's less like everyone works at NASA, you know.
My school was literally called like NASA Space Center, like
Yeah, exactly.
Space Center Intermediate, like
Yeah,
come on, like it was right on the nose. It was like a 10-minute walk from the Space Center. I'm middle school.
yeah, and we can see the Saturn V from our house just because they have it in rockets.
Yeah, yeah. When I was in Houston last, I went to go visit one of the Falcon Hinds, which was really cool. Yeah. So going back to, and I know we're running over, so I appreciate giving me a little bit of time. Going back to the CTO or the team, one question I had, and it might have been vague on the website, but it said that the CTO had 90% of voting rights for the company or something like that. I just want to ask what that was about.
Say that because that is incorrect.
It said, yeah, it was kind of like, that seems a lot.
No, so for full public disclosure, it's equal, me and Mumbit.
Okay, let me pull it up where I was looking, and I can
it might have said the founding team has that percentage of voting rights. That would make.
I think it was Space Ventures, and then if you go to invest and then cosmic shielding.
Yeah.
So if you go there, and then maybe it was on company, and I can edit all this like Googling out, but 97% voting. Yeah. So if you go down on like the risk disclosures, sorry, it was 93%. So it was Yanni and CTO who holds 93% of outstanding shares of voting. So I just want to clarify what that means.
Yeah. So it's both of us together.
Okay. Okay. I wasn't sure if he was like, if he had full control or
something. No. Like, okay. Yeah. It's together. It's equally split between us. And now it's less because, we have the employee options in there now. Investors coming in, but yeah.
Okay, cool. And then how did you and the CTO meet? Like, what's your background? What's your first startup? And why are you kind of doing all this?
Completely different. So I've always wanted to get into space. I'll give you a background. I've had the benefit. Both my parents are physicists, astrophysicists. So they deal with super theoretical stuff, non-applied, right? Just very, very, out there stuff. So when I was young, I always wanted to get into like my goal was like, my dream back as a kid was getting into something like very exotic propulsion, like non-chemical, right? Because I think chemical is a short-term thing. I think I was excited about plasma rockets and things like that, right?
Yeah.
But I always thought that'd be very far out. When I went to Georgia Tech, I was doing biomedical engineering, very different. And then my first startup it was like a home sharing social network, right? It did decently well for a while. Like we got funded, we had a little office, and it grew okay, but we couldn't really figure out how to make it profitable. And then eventually, kind of attrition took its toll.
What was the strategy for that?
It was so with the background on like why we went through the social home share. Okay, so basically, at the time, Airbnb, we were in at Georgia Tech. You're in the South. You see a lot of football travel, right? So me and my friend were like, oh, we should start a company that does look like a social chat marketplace, basically, where you can find places to stay at other colleges without having to worry about staying with an old guy like Airbnb. You're not going to have to pay $2,000 a month. At the time, though, Airbnb had way fewer hosts than they had now. Like for example, they had I think 500,000.
Oh, okay.
For an entire platform to have that, of course you're going to try to compete with them. Why not? Especially when you're like a 20-year-old college kid, you're going to be like, hell yeah, I'll jump.
Yeah, we can beat those guys.
Yeah, exactly. So the idea, though, and this is something that's still the case, those marketplace platforms they had a problem for a long time where they weren't profitable because, you'd hope once your user base gets to a certain size, you get this network effect that basically drives the acquisition cost below your return on users. Very simple economics you'd hope would happen, right?
Yeah.
Happens with social networks very quickly if they work, right? Which most of them don't work. But if they work, it usually happens very quickly. And because there's a huge network effect driving down your acquisition costs. Now, for some reason, the marketplace platforms like Uber and Airbnb, right? That was just not the case. And I honestly don't know if they managed to fix it recently. It was the case for years, right? Yeah. Where they were actually losing a lot of money per user, even when they got big to the $1 billion level, right? Mm-hmm. They had to balance it out with other ventures and so forth. So I was like, what the best way is if we were to compete with these guys, and I was like, if we had an audience with a really high virality coefficient, people who are always seeing each other doing, just always mixing with each other, college kids, right? Mm-hmm. And someone that we could easily access, which is that same market, right? Then maybe, and if we developed it from a perspective of social interaction and visibility, then maybe we could focus on that issue first rather than focus on the supply, right? But maybe have a lower acquisition cost. And we did. Our user acquisition cost was not that high. And so the idea was that basically you create a geographic social network. So like, people started using it to like, we looked at the analytics, people would be like driving from, Birmingham and going to a game at LSU and saying like, hey, where do people go out at LSU? Even if they don't actually use the app to book, which was interesting. Really helped engagement and so forth. However, like I said, the key is, especially in the East Coast, it's not very easy to get funding for business consumer technologies, software, like social networks, especially, or marketplace software. However, we did manage to get some good funding. But again, like I said, it was a matter of being able to be nimble enough, fast enough. And I can speak on that for that.
Yeah.
Also, the team was kind of like haphazardly put together, just a bunch of friends. We weren't actually, it wasn't like calculated. This was much more calculated.
So then you learned from that. And what did you do after? So then you kind of closed it down and then started this, or?
Yeah. So there was like a year and a half gap between these two, where I kind of just did like a lot of consulting for one of our old investors who actually did end up following on to this company, by the way.
Nice.
And just like freelance stuff there, here and there, but also just taking time to just like, plan out the next step. I wanted to get into like, I was doing a lot of like research into carbon capture technologies using like bacteria and like maybe like a methane capture systems. And I was like interested in all sorts of random things, right? But then I started getting wind of the new space economy again, right? And I was like, oh, there's a lot of activity going on, right? So then I remember when I was young, my dad worked in fundamentals on cosmic rays, not like shooting, but like very, very basic physics on like, determining the sources and so forth. And he also worked with the extremely high energy ones that we still don't know where they come from, like the super GCK, they call it. If anyone ever wants to look that up, it's kind of mysterious stuff. It's kind of cool. But I was telling him about this, and I saw the Starship from SpaceX. I went to him and I was like, hey, when I was I remember you always talking about these metals being an issue, right? And he was like, oh yeah, why? And I was like, SpaceX, they're building the Starship out of steel? And he was like, what? Why? I was like, good question. Well, I personally think, by the way, just as an aside, I personally think they're only doing that for prototyping. The real one isn't going to be made of steel.
Really?
I don't think so.
You think I build a material like this? Or
I hope they don't build one like this.
Yeah. you mean like you want?
I think they'll go for something lighter because, from my perspective, why would you build steel's cheap, but like it's heavy, right? And also it's extremely, extremely bad for radiation, right? Like it's like an understatement. But if you can make your engines can do what they need to do, all this like fancy, landing and like thrust vectoring and so forth with steel, right? And you put on an extra engine for your prototyping, and then remove you not have to worry about building a fancy like actual hull for the spacecraft, right? And that's what you use for your prototyping phase. You're not using the most cutting edge Starship every time. They're not putting the inside in, I bet. They're not making the capsule actually have the amenities you're going to have on like and so, so I think it's just a stopgap, and this just steel's cheap. It's really.
You think they could? Is there like a paint that could reduce radiation?
So paints, there's not for particle radiation, really.
Okay.
Not like
so. There's need. So maybe like they could use your material like to coat the outside of it,
or in the inside. It could work, right?
Okay.
If I'm wrong though, and they're actually sticking with the steel, then I guess you'd have to use some other layer, right?
Yeah.
But I personally don't think they're sticking with steel. I think that's just for cheap.
That's interesting. Yeah.
Yeah, because like think about it like this. Like if you're testing the crash dummy cars, you're not actually building, like you're not painting the car. Yeah, they're just using like a body, testing the body of the car.
Yeah.
And like, why use an expensive, aerospace grade alloy for the body? You could use this steel. I could be absolutely wrong though. So I'm just talking, I'm just thinking.
Yeah.
So I told him this, and he was telling me like about the old research that his team did, and his team relating to Lembit. They worked together way back. So I spent like the summer doing a lot of just research, reading all these papers back and forth. And the more I started reading about some of the work they did back in the day, I was like, oh my God, there's a big opportunity here. They really didn't solve this, right? And people are just ignoring it. And then I started talking to big I started like, doing some little research in the market, talking to big guys of what I thought were the big guys in the, new space companies. And I'm not going to name any names, but people were like, oh yeah, we solved it. Like they were being such like to be such pricks about it. Everyone was just like, yeah, it's been solved. And I'd ask like, oh, what are you using? And some people like, oh, we tested lead on blah, 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 or tantalum on blah, 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 or these heavy metals and it works perfectly. There's actually no issue. And I was like, okay, the fact that that's their answer means we are good to go. This is the perfect market to jump in. They said lead, they said tantalum. And I was like, these are guys that are, they're making big decisions in the industry, right? Mm-hmm. So I was like to my dad, I was like, can you give me the emails for like Lembit and some of the other guys who were on these papers? And then he did. I reached out to Lembit and I was like, hey, and this was funny because he's like, this world famous physicist, has gone to every major university in the US, in the world, like, done like lessons and so forth, big awards and all this. And I was like, oh, I messaged this guy and I was like, hey, so I got a startup funded once before. I think this one's going to be easy if we kind of team up, right?
Yeah.
Easy to get from and easy to start. So we spent a few months just talking back and forth. And then he was like, I know the perfect group to help us with like materials development on X and Y. And then I was like, oh, there's this one guy who does the heliophysics who might be useful. And then it all came together like that. And then
nice.
Yeah. So and then eventually
you started raising.
Yeah. And it was hard at first, very, very, very hard at first. So we formed the company on August 7th, 2020, right? And yeah, things were not going too well at the beginning because I could not figure out like how to raise for something like such like this deep tech new space. I didn't know I knew the scientists at that point. Lembit and I mean, mostly Lembit to be frank, had the network for the technical team and the scientists in the industry, like people pioneering space for decades, and even the new ones, right? But not the money. So I was like, oh, I need to get in contact with the right people. So kind of had to start from scratch. I thought my funding, the investors from my last company might have connections in the new space industry, or I might like give me a head start. Not really did not. I had to just cold message people on LinkedIn, like, and a few guys, like some people from Space Fund. And
it's amazing to me that you did not use Twitter and you've already gotten this far. So it is amazing.
Yeah.
I'm like listening to you and I'm like, yeah, I know like immediately the VCs that I would message and like I'm mutuals with them, like all this stuff, just because I have like put hundreds of hours into Twitter, but like I just like immediately am like not concerned about like connecting to those people, but like I'm impressed that you cold emailed them and like got this. And that's my mini Twitter rant.
I appreciate that. And like, again, for everyone listening, I did not have a Twitter until last week. So
I'll link it below.
Jack kind of made me get one. And I was like, all right, let's get a Twitter. I will say you're right. I do need to start, posting things. I need to start. There's a lot of really cool stuff that we do and really cool implications, really cool. Like, I mean, one thing, like I said, we're a hot company right now for a reason in the, in the client space and VC space. And it's because somehow we actually managed to get this far and produce a material that works in a lot of applications. And, we're actually, we have the capital now to be flexible, and no, I think it's just really exciting. I mean, the next few months are going to be crazy. The next year, who knows? Our goal is to go for a Series A by the end of next year with these little purchase orders that are coming in now, just sample tests, right? Assuming that they check out, assuming our results aren't wildly inaccurate, which again, right, they're not. Right? I guarantee you, they're going to be pleased. I think that we are actually on track for some serious growth in the next year, unless something catastrophic happens, which you never know, right? Who knows? Maybe there's a massive solar flare. No, I think I'm really excited.
I actually, just one last quick question. Axiom, they're putting up like a habitat kind of thing, or they're trying to with the modular habitat. What material are they using?
So they're actually, it's not a shielded habitat yet.
Okay. Oh, wow.
But from what I know, right? I think Thales is subcontracted out to build it. Okay. Thales. And it's just like the same materials as the ISS.
Okay, cool. Yeah, that makes sense because they come from the ISS.
Yeah.
But anyways, I didn't mean to detract from the ending.
No. And I will say, Axiom's not unaware of the problem. I'll tell you that.
Okay. Yeah. I figured there might be a smile there. Cool. Was there anything else that I should have asked? I feel like we went through Earth applications, in-situ resource, carbon capture, like solving microplastics, and then like evaluation, raising money, the team, background, your background, the recurring revenue from solar engine. Just kind of summarizing a little bit, but I think was there anything else or?
No, I think that pretty much hit everything for now.
Oh, well, I guess the call to action is the last thing. So what do you want?
Oh yeah. So again, if you're listening and you do want to kind of take part on a little journey here, we are listed on Space Ventures for a $1 million allocation of our current $8 million round. So feel free to go and invest if you'd like.
And it's valued at?
It's valued at, we're doing a $50 million valuation cap, which is important to know. That's a valuation cap. So it's not the current valuation. It's just that what we're expecting to hit in the next few months. And yeah, we've got some of the best technical partners, VC partners, and now clients on our backing us. So we're excited for how things go and where things will take us over the next year. So
awesome. Yeah. Awesome. So the link to the crowdfunding will be in the description. And then also Yanni's Twitter will be in the description, as will mine as well, NASJAQ__. And I'll see you guys in the next one. And this was an awesome conversation. Thank you for the time.
No, it was fantastic. And I looking forward to talking to you again, Jack.
Awesome. Yeah. I actually, so I want, you know how Joe Rogan has guests on multiple times and you get to know them over time. That's what I want to do with founders. So we have this episode now of where you are now. And then, in the future, you get to see you grow and all that stuff. And that's what I really want. I think that's really important.
Yeah. I've got a few colleagues too that might be good to talk to. I'm not sure, Space Forge by any chance?
Doesn't ring a bell, but yes, I'm definitely open to some connections and also the connections to the founders as well.
For sure. 100%.
Yeah.
All right.
I'll message you what they're doing.
Awesome.
Too.
Perfect. Awesome. And feel free to, whenever you get the chance, let me know about those two connections you're interested in.
Yeah.
I'll take, it's always
for sure.
Awesome. So I hope you guys enjoyed that. Like, comment, subscribe. Tell me what you thought was cool. Tell me if you're investing. Let me know if you have any questions and I'll try to answer them in the comments. Subscribe for the next podcast. My next podcast is actually going to be on some crypto stuff with the future of algorithmic stablecoins and these beans. If you've been on Twitter, I've been tweeting about some beans and I got these bags and I have way too many beans. So I needed to learn more about it. Anyways, I'll be doing more hard tech startup podcasts, but I'll see you guys in the next one. Peace.